Okay, so let's take a look here at a couple of examples coming from the 2.6, this implicit differentiation. And what you have to keep telling ourselves now, what makes this an implicit equation, notice that the x's and y's are on the same side of the equation. What that means is that explicit equations are in the form of y equals something in terms of x. But these equations would be quite difficult to express y equals. So the implicit differentiation means that we're going to take the derivative with respect to x of both sides. However, when you're taking the derivative of terms that have y's, then by the chain rule, we're going to add that factor of a dy. So let's just take a look here at a couple of these. We cannot take a look at all of them. So let's work number 12. And number 12 would be similar to number 19. And then I also want to take a look here as finding the equation of a tangent line. So we'll take a look at a couple of these. We'll see how much time we have. Okay, I'm trying to keep these videos to be short. Well, because of the upload. So let's take a look here at number 12. Pull you back on the screen. Center. Okay, so when I'm reading this, you have cosine of xy, which is a product. So cosine, you have inside function. I'm going to have to use the chain rule. And then we're able to take the derivative of these terms. So you don't need to do this, but some that are just practicing, we're taking the derivative with respect here of cosine of xy, and then we are taking the derivative with respect to x of 1 plus a sine y. Again, you don't need to write this step, but when you take the derivative of the outside function, the derivative of cosine is a minus sine evaluated at the inside function times the derivative of the inside, which is a product, so you're going to have to use the product rule. So the product was f here, and this would be g. So in this case, f prime will be 1 times g, which would be y, plus f, which would be x, times the derivative of g. So you take the derivative of y, which is 1, but that's where we're adding the dy dx here. And now when you take the derivative of a constant, you get 0. And the derivative of sine y is going to be a cosine of y. But we're taking the derivative of y, so by the chain rule, we have to add dy dx. And this is where it becomes a little bit more work here. And the reason why is that you have dy on both sides. So this is similar to solving an equation, meaning you're going to have to distribute this term here, distribute this term here. So this is going to be a minus, this is going to be y, this is going to be sine of xy, this is going to be minus, this is going to be sinus, I'm having sinus problems, sine of xy, and this is going to be dy dx, which is going to be cosine of y dy dx. Now, I recognize that it might just be easier to bring this term over to this side. So this would be a minus y sine of xy equals, and then this would be a cosine of y dy dx plus a sine xy dy dx. And now dy dx here is, you consider it like a factor. So what are we going to do here? We're going to factor the dy dx out. Oh, so what this is going to be is it's going to be a minus y. This is going to be sine xy. And then this is going to be cosine y plus sine of xy times dy dx. And now since this is a factor, we're going to divide both sides. So you're going to get a minus sine of xy, which is going to be divided by a cosine y, plus this is going to be a sine xy equals dy dx. So when you're finding the derivative of an implicit equation, it is going to require multiple steps. You got to keep track of things. So someone mentioned, using color. Color is a great additive tool to help distinguish. And you also have to know when are you going to use the dy dx notation versus when do you not, right? So there's a lot of pieces that we have to kind of keep aligned here. Now, in this next grouping of questions, number 25 through number 32, use implicit differentiation to find an equation of a tangent line to the curve at a given point. And so I don't like doing the odds because you do have the solutions to them. So let's go forward here and let's take a look here at, let's say, they all look good. Let's do number 28. And in pre-calc, we talked about, graphing the conics. There you go. And it's the hyperbolas and the ellipses. And now we're finding the equation of the tangent line. And so when you take a look here, let's see if I could do this without messing things up. So if I just take this piece, good, and then drop it over here, then what do you have? Well, you're going to have the derivative of x squared, which is going to be 2x plus, now you have a product. So I'm going to call 2x f, and I'm going to call yg. And so we have the derivative of f, which is going to be a 2 times y, plus you have 2x times the derivative of y is 1, and then you get dy dx, plus this is going to be an 8y dy dx, which is going to equal the derivative of a constant is 0. Now, this one is just asking us to find the equation of the tangent line, which we need the slope, which is expressed as the dy over dx. So at this stage of the game, it's not necessary for me to go and solve for dy dx like I did the previous problem. So in here, if you put x to be 4, if you put x to be 2, you get 4. If you put y to be 1, you get 2 plus x, you're going to get a 4 dy dx plus 8 dy dx equals 0. So then when you add these, you're going to get 12 dy dx is going to equal -6. Divide dy dx is going to be a -1/2, which represents the slope, and therefore you get y minus 1, which is going to be a -1/2 x minus 2. So when you distribute, this is going to be y minus 1, which is a -1/2 x, which is going to be plus 1, and you get y equals a -1/2. Let me write this clear. This tablet is problematic. So you get a -1/2 x, and then you're going to get plus 2. I noticed on our previous game that some folks were leaving it in this form, but we always express our tangent lines to be in the form of y equals mx plus b, which is slope-intercept form. And as you see with these problems, they're similar, but they're different. Like number 29, you're going to have this cardioid that you spent time graphing in polar coordinates. Look at here, you're going to have to use the chain rule, embed it right in that problem. So this is, where that practice and the level of, where that player wants to strive for is how many problems do we practice and understanding the different algebraic techniques embedded in the problems. So I wanted to take a look at an example of that form.